Okay, so this week, Module 10 is signal, contrast, and noise, and I'm going to be recording the topics this week, just as a little different format. I think some of the written notes weren't very clear, some of the figures weren't very clear, so I'll go through the topics this week using this format. So first, what are we going to do for this topic? We're going to look more closely at the voxel signal itself and the noise in the voxel. We're going to talk about how to measure the signal to noise ratio in a MR image, and we'll talk more about where the noise comes from, the distribution of the noise in a magnitude reconstructed image, and then from there, later on we'll get into contrast. But for this topic, we'll stick to just signal and noise. So, talking about the voxel, what is a voxel? We've talked about this in previous modules a little bit. A voxel is really a volume element. So when you're looking at an MRI image, each pixel is really a volume element that has a certain length in x, which is typically this direction, a certain length in y, and a certain depth, or z, in the z direction. So in a 2D imaging case, the z direction is a slice thickness. In the 3D imaging case, you just have another dimension to your voxel. So obviously when you're looking at an MR image, you have to be able to tell between the signal and the noise. Otherwise, you just have a noisy image and you're not going to be able to make heads or tails from different tissue types. Therefore, it is important to know how the raw data gets translated to the image data. So we can look at another equation for the signal given here, where this term out front is really m0. So what we have here is, this equation is very similar to one of the equations that we had that I showed in Module 5. So the signal is proportional to m0, the square of the main magnetic field, and the receive field, where this parentheses means showing the positional dependence of the receive field. And these integers, p, q, and r, are just saying where in the image you are in x, where you are in the y direction, and where you are in the z direction. So that's just showing you some spatial dependence on the receive field. And this is all multiplied by the volume of the voxel. And so what about the noise in MRI? Again, to observe the tissues of interest, there has to be enough. There has to be actually a lot more voxel signal than there is noise. Most of the noise is coming from random fluctuations in the receive RF coil electronics and from the sample itself. So we have these random voltage fluctuations in the sample. The human body has molecules that are bouncing around and Brownian motion. So we usually look at what's called the variance of the noise using this pretty simple equation here, where R is an electrical resistance and BW is the bandwidth. K is Boltzmann's constant and T is temperature. So for R, we usually split that resistance up into three components: the resistance due to the body, or the human body, which is the sample, the coil, and the electronics that are either inside the RF coil or kind of beyond the RF coil, such as the preamplifier. And it's also important to know that the noise that the receive coil picks up manifests itself as noise with equal variance throughout the entire image. Remember that the signal itself is one-dimensional, and when we sample the signal, we're well, in order to go from a sampled signal to image space, we have to take the discrete Fourier transform. And when we do that, the mathematics of the discrete Fourier transform, or the DFT, results in the noise. Well, not just the math, but obviously the physics of it as well. That result, when we're going from the signal domain to the image domain, the noise gets spread throughout the entire image. So here I'm showing probably one of the first example images, and as I've shown here, I've kind of given it away. What this is, it's an axial slice through a kiwi fruit. So one of the first things you do when you look at an image is just see contrast. The human eye is very good at seeing contrast between colors and shades of gray. So look at this image and think, how good is this? Is this a good image? Is this a bad image? So for example, if you look up here on the corners, if you look closely, you can see this snow, or the noise, or the noise floor. So being able to actually see the noise is usually not a good sign. So although you can make out the seeds and the different structures in the fruit, being able to actually see the noise floor indicates that maybe the image isn't as good as it could be. So here I'm listing the imaging parameters. The field strength is 7 Tesla, TR repetition time, TE echo time, FOV is field of view, a matrix is 256 elements in the X direction by 256 elements in the Y direction. So, and the slice thickness, so that tells you that this is a 2D image. So the Z direction, although you can't see it because it's volume averaged into each pixel. So the Z direction is 1 millimeter thick. I guess you could say the matrix is 256 by 256 by 1. And the other parameter is NEX, which is number of averages, which is 8. And the acquisition time was about 2 minutes. So before we get into how the signal to noise ratio, or which is a very common metric for qualifying images, it's important to know how the noise is distributed in the image, because what you might do as a naive approach to calculating the signal to noise ratio is to take the average signal and then divide it by the average noise. The reason you cannot do that is because in a magnitude image, the noise is distributed according to the Rayleigh distribution. So here I'm showing a histogram of the pixels in the white region, or part of the noise region, not the entire noise, but because obviously there's noise over here as well. But it indicates this this distribution. So if we had a Gaussian distribution, we would have something like this. Go up and down. And Gaussian would have a zero mean. But here you can see there's a much different distribution. So then in order to take the signal to noise ratio, to calculate that, we have to take the average signal and divide it by the standard deviation of the noise. So in this particular image, I've taken as a signal as much as the contents of the fruit as I could, and as the noise, I created the region of interest out here. This is the noise ROI, and I just divide these numbers: the signal mean divided by the noise standard deviation gives me the SNR. So 14.5 is, as we expected, it's pretty low. I don't know if there's a particular number, but yeah, I think most radiologists, I've heard numbers around 30 is the lowest. And there are ways to ensure that your MRI machine is returning appropriate levels of SNR by doing calibrations or quality scans each morning before the patients are scanned. So how can we improve that? Well, as I mentioned before, for that particular image, I did 8 averages. We could very easily do more, but there's a trade-off, because in order to improve the SNR by averaging, you have to take into consideration that SNR improves only as the square root of the number of signal acquisitions, or NEX. So let's say the number of signal acquisitions goes from 1 to 2, then I've increased my SNR by the square root of 2, which is only 40%, but I've doubled my scan time. Now if I go from 1 acquisition to 4, I've improved my SNR by the square root of 4, which is 2, so I've doubled my SNR, but I've quadrupled my scan time. So then, right, if I go from 1 to, or let's say for example I go from 4 to 16, I then again double my SNR, but I've increased my scan time by 16 times from the original 1 acquisition. So you see clearly that it's not practical to use averaging as your only means of increasing the SNR in an image. The clinical scan really has to be around 45 minutes at the most. So you have to find other ways to improve the SNR, and there are other ways to do that, and we'll talk about those in the next topic.